Alright, so our last chapter this semester will be Chapter 10. Chapter 10 continues talking about chemical bonding, but here we're focusing on covalent bonds and how we can take a Lewis structure and turn that into sort of a three-dimensional picture of that molecule. At this point we haven't cared a whole lot about how we draw the angles on Lewis structures, but now we're going to take a little bit more care about what those angles are, and we're going to try to interpret what the shape of that molecule might be given the Lewis structure. So, let's take a look at some examples. Again, this is chapter 10 in our textbook. So, the model that we're following is the valence shell electron pair repulsion model, or theory. And so, valence shell, those are the electrons that we're interested in. Core electrons don't really contribute to bonding. Valence shells of the electrons are the only electrons that really do anything in terms of bonding with other atoms. So we look at valence shell electrons. And then we're looking at electron pairs. Remember we talked about how it takes two electrons to form a chemical bond. And so each pair of electron is a bond for us. And so we're going to look at how those pairs of electrons interact. We're also going to pay attention to the lone pairs of electrons that don't do any bonding because they do contribute somewhat to shape. And then the last part of this theory is the repulsion part. Remember, electrons are all negatively charged, and so all of our electrons don't want to be on one side of a molecule. They want to be as spread out as possible because the negative charges will repel each other. And so we're talking about valence shell electrons. We're looking at electron pairs, including lone pairs and bonding pairs, and the geometry is determined by how those pairs repel one another. And so in our first simplest form of molecule, we have a linear molecule, Ab2. When we talk about molecular geometry, and when we use this VSEPR theory, we can only do it around specific atoms. We can't determine the structure for a whole molecule unless that molecule only has one central atom. And so in all of these examples, A will be our central atom, and B will be all of our peripheral atoms. And so here, A is in the middle. We have two atoms that it's bonded to. So the second column is the number of atoms that are bonded. The third column, the number of lone pairs. And so it looks something like this. Here we have A in the middle, B bonded on both sides. If we just have two pairs of electrons, the farthest apart those electrons can be is 180 degrees, right? That's the farthest apart they can be. If we have a 180 degree bond angle, it's going to be linear, right? And so we have a 180 degree bond angle. Now in each of these categories, we're going to give two different geometries. Here you'll see the arrangement or the geometry of the electron pairs, and in this last column, the molecular geometry, or how the actual atoms are arranged, not including lone pairs. Right? Just a note, on Moodle, I uploaded a worksheet. I understand if you can't print it out, but if you're interested, go through and try to duplicate that, and it's a great study sheet. If you fill that out, you can know what the different shapes are based on how many atoms are bonded, how many lone pairs they have, that kind of thing. That's going to be key information for our final exam. Okay. An excellent example of this is beryllium chloride, BeCl2. We have a beryllium in the middle. We have a chlorine on each side. Remember, beryllium is one of those exceptions to the octet rule. He is A-OK with only having 4 electrons, and here he does, 2 in each bond. And then the chlorines have their octet satisfied, and we have a 180 degree bond angle. So moving on, I just had 2 peripheral atoms. Moving on to 3 peripheral atoms. We call this trigonal planar. Right? And so the trigonal comes from the fact that it's all in a triangle like this. Right? I'm just gonna copy over that, right? And planar because all 3 of those molecules lie in the same plane. Maybe you remember from a geometry class that any 3 points define a plane. Right? Here we have 3 points around our central atom, those 3 peripheral atoms, and they define the plane of that molecule. And so a trigonal planar atom is a triangle design, and it's in one plane. And you see the bond angle of 120 degrees. Because there's no lone pairs, this trigonal planar is also the geometry for the molecular geometry and the lone pair or electron geometry. A good example of this would be something like BF3. BF3 is a molecule that has boron in the middle, right? With 3 fluorines around it. That boron, again, is an exception to the rule, and so he's okay with only having 6 electrons. Another fairly common version of this would be something like nitrate. Right? You had to draw the Lewis structure for nitrate. It's likely that you have to draw the Lewis structure for nitrate in Alex. And nitrate ends up looking something like this. He has resonance structures, it's true. I'm going to skip those resonance structures for now. He's got a 1- charge. But you can see there are 3 groups of electrons. Right? Now this double bond, even though it's 2 pairs of electrons, it's 1 electron group. It's 1 double bond, right? And so we count it as 1 group of electrons. And so even though it's a double bond, since they're in the same area, right, those electrons are between that nitrogen and that top oxygen, that's counted as 1 electron group. And so this guy is still considered trigonal planar. But what if we go from there, and instead of having 3 peripheral atoms, we only have 2 peripheral atoms and a lone pair? What would look something like this, right? Our textbook uses A again for that central atom, B for those peripheral atoms, and E for pair of electrons, right? That lone pair of electrons. And so what we end up with is this. We have the B, the peripheral atoms at the bottom, our central atom in the middle, and that lone pair up here. When we draw or sketch out a lone pair, sometimes we put this sort of bubble around them. That's just to show they do in fact take up space. They're not just little dots on a page. They do take up some space. And so SO2 here is a good example. You'll notice each of these is a double bond. I don't know how well that comes through on the video. But each of these is a double bond with that lone pair, and so sulfur has 10 electrons around him. Sulfur is one of those that is a good exception to the rule because he can put extra electrons in his empty D subshells. Okay. If we had 1 atom bonded to the central atom, anytime you have 1 atom bonded to another atom, right, it's got to be linear. There's no other way to do that. And so if we had A, B, E2, 1 and a 2, right, that would be something like this. I guess I should put 2 lone pairs around him. Anytime we only have 2 atoms, obviously it's going to be linear. And so we won't see any of that on the rest of these tables. So moving up from 3 peripheral atoms to 4 peripheral atoms, we have a new shape, tetrahedral. That term comes from the fact that it's 3 faces. If you look here, it's hard to see, but we have a face on the right of this triangle, and then there's a face in the back, right? In the back of that structure, there's a face on the left, and then there's a face on the bottom. And so there's 4 faces, tetrahedral, and so that's where that term comes from. 109.5 degrees, kind of a weird number, but that's the angle at which those 4 points can be spread across a sphere that they're farthest apart from one another. A lot of places will round this to 110 degrees, so just depending on where you look, where you see, you may see this listed as exactly 109.5. You may see it listed as 110 degrees. I think the ACS exam tends to use 110 degrees. And so just those are essentially the same thing. You don't have to say, oh, well, it's not 110, it's 109.5. We'll just leave it at 110. Okay. Again, because we have no lone pairs, the molecular geometry matches that electronic geometry. Okay. A good example of this is methane, right? CH4. One of our simplest hydrocarbons. We have a C in the middle and then 4 hydrogens around it. This is the first time where we've truly had a three-dimensional structure. For something that's linear, we can obviously display that in 2 dimensions. For something that's planar, trigonal planar, we can display that in a plane, that's 2 dimensions. Now's the first time when we really see things that are in 3 dimensions. And so you'll notice here that on our tetrahedral structure, we have this wedge that comes forward, and we have this dash that is trying to represent going backwards. And so in real life, what's happening is those 2 hydrogens are in front and behind one another, and we can't draw them both without rotating the molecule a little bit. But if we rotate the molecule a little bit, then these 2 would not be in the plane of the paper, right? And so what we do is we represent the one coming forward at you as this wedge, we call it. And so I'm going to draw that one bigger for a little perspective. And the one that's going behind the paper or behind the slide or into the screen, that one is on the dash, and he's going to be a bit smaller, right? And so we've got these 2 that are in the plane of the screen. We've got one coming forward that's a big H on a wedge. We've got one going backwards that's a little h on a dashed wedge. I call them wedges and dashes. Other people call them different things, but a wedge and a dashed wedge. You do not have to draw them with a big H or a little h. I just try to do that for some scale. But I would like you to start thinking about sort of how we should represent these in 3D. And we'll see more examples of these as we go through the rest of this discussion. Okay. All right. So what if we start replacing some of these atoms with lone pairs? If we have one lone pair, notice that the electronic arrangement is still tetrahedral. There's still 4 groups around that central atom, and so it's going to stay tetrahedral. But our molecular geometry becomes trigonal pyramidal. So we've got that tetrahedron shape, and we just pluck off one atom and replace it with a lone pair. The actual arrangement of the electrons doesn't change, and so instead of being planar, we have just a slight angle now between this central atom and those 3 peripheral atoms. This is ammonia, NH3. If I were to draw this as with those wedges and dashes, I would keep the lone pair in the plane of the screen, so I don't have to try to draw that lone pair on a wedge or a dash. And so I'd have a wedge coming forward for hydrogen and a dash going backwards for hydrogen over here. And again, if you want to draw that bell around the nitrogen, that's fine. Or around the lone pair, that's fine. With 2 lone pairs, we have a very familiar example. This is water here, H2O, right? And you can see that he's got this sort of bent shape, and so that is the molecular geometry for water for any compound that has a central atom bonded to 2 atoms and with 2 lone pairs. Right? Because we don't really care a lot about the shape or sort of the position, front or back of lone pairs, we would write water just like this, try to keep that angle, and then those lone pairs, one's in front, one's in back. We don't really demonstrate that. We only care about the position front or back for atoms, not for lone pairs. Okay? Okay. So we've been talking all along about adding on lone pairs, but adding lone pairs actually does something to the geometry. Not only does it change the name we give it, but it does something else, especially to the bond angle. And so let's talk about that a little bit. When we were talking about methane, right, this is our CH4, our methane, he's got no lone pairs. And so this is a perfect 109.5, right? That circle is a little bit off, but it's 109.5. In ammonia, NH3, we do have a lone pair. And it turns out that that lone pair, because he's not stretched between nitrogen and another atom, that lone pair tends to ball up. Look how this lone pair is sort of fatter than these electron areas here. Right? And so what that means is that he's actually sort of occupying a bit more space close to that nitrogen, and he's causing those hydrogen atoms to sort of push together. And so notice that this angle is just ever so slightly smaller than the angle in methane, 107.3 versus 109.5. Now, I am not asking you to memorize these angles, but just recognize that if we have lone pairs, the angles get smaller, right? Now, obviously, this angle gets larger, right? I'm just going to say greater than 110 degrees, but this angle gets smaller, less than 110 degrees. In water, where we have two lone pairs, again, those lone pairs occupy lots of space, right? These are fat lone pairs, and so they push these two hydrogens together, and that's 104.5 degrees. And so that's, again, less than 110 degrees. Okay? And so this lone pair repulsion, like we have in water, right? This repulsion between these two is greater than lone pair bonding pair repulsion, right here, which is greater than bonding pair repulsion. And so because not only do these take up more space, but these two here are repelling each other, right? And so the fact they're pushing each other farther apart means that these hydrogens have to make room for them, and so these hydrogens end up getting closer together. And so the moral of the story is, the more lone pairs you have, so if we increase the number of lone pairs, LPs, right, we decrease the bond angle. This is also true for double or triple bonds. Going back to our example of nitrate, here's our Lewis structure for nitrate. It turns out that instead of all of these being 120 degrees for a trigonal planar, this bond is a little bit more than 120 degrees because that double bond repels that single bond a little bit, and these is a little bit less than 120 degrees. Right? So anytime we have more electrons in a particular region, they're going to push bonds away from that space, and so this top angle becomes more than 120 degrees. This bottom angle, that's where they get closer together based on the pushing of that double bond. All right, moving up to 5 central atoms. This is trigonal bipyramidal. So if you can see in the middle of this structure, we have a triangle. Okay? And we have a triangular pyramid on top and a triangular pyramid on bottom of that sort of equatorial position. And so that's where the name comes from, trigonal bipyramidal. We do have different terms for these positions. These are equatorial. Okay. So these 3 positions here. And let me change colors real quick. The position at the top and the position at the bottom are called axial. Okay. So just like the Earth spins on its axis and the equator goes through the middle, the blue positions are the axes, the axial positions that it spins around, and the red positions are that equatorial positions that stay in the middle between those two top and bottom positions. Okay. Between the axial and equatorial positions, you see that there's a 90-degree bond angle there. And between these equatorial positions, that's essentially a trigonal planar molecule connected to a linear molecule, right? And so we have that trigonal planar we know is 120 degrees, and then that linear molecule is sort of bisected, and so it's 90 at the bottom and 90 at the top. Okay? A good example of trigonal bipyramidal would be something like phosphorus pentachloride, PCl5. One thing to note, now that we have 5 atoms bonded to that central atom, we can't do this with anything in the n equals 2 row, right? That period doesn't have those empty d orbitals, and so the central atom has to be something with an expanded octet. So phosphorus is in the n equals 3. He's got those empty 3d orbitals. He's happy to expand his octet, and PCl5 is a good example. Again, you can see here we've got these 4 atoms are in the plane of the screen. We've got this atom coming forward, so he's on a wedge, and this atom going backwards, so he's on the dashed wedge. Right? So what happens when we replace some of these atoms with lone pairs? The most the most creative name that we get, our textbook calls it a distorted tetrahedron. They also mention in there that this is called a seesaw. That's sort of the more common name. This still does have 4 faces, tetrahedron, but the seesaw is a much more common name. If you think about it being on a surface this way, this atom and this atom behave as sort of the feet, and then you can rock it back and forth like this, like a seesaw. Right. If we think about what this lone pair does to bond angles, you can see that this is not a straight line, right? It's pushing those atoms in just a little bit. And so this angle is going to be ever so slightly less than 90 degrees. And this angle is going to be a little bit less than 120 degrees, right? Because we have that lone pair. We pulled off of the equatorial position first rather than an axial position, because this axial position has 3 90-degree interactions. The equatorial position only has 2 90-degree interactions. Let me change colors again. The equatorial position only has 2 90-degree interactions, one here, and then 2 120-degree interactions. I know that's getting hard to see. But so I'm going to write it out. The equatorial has 2 90-degree and 2 120-degree. The axial has 3 90-degree interactions. It just turns out that it's lower in energy for that equatorial position to come off, because on average those interactions are farther apart. Since he's only got 2 at 90 and 2 at 120, those are on average farther apart than the ones got 3 at 90 degrees. And so equatorial atoms are the ones that get exchanged for lone pairs. You'll see that our second lone pair comes off in an equatorial position as well. And we end up with a T-shaped molecule, right? You can imagine this being T-shaped right there. Again, notice that this is bending in a bit, and so this is going to be less than 90 on the top and the bottom. We have no more 120-degree interactions because both of those positions have been replaced with lone pairs. If we took off another one of these positions, right? So if we took off and replaced that third equatorial position with a lone pair, we'd be back to a linear orientation, right? Because all we'd have would be the central atom and those 2 axial positions. For the last one, with 6 bonds to a central atom, again, this has to be an expanded octet situation, and we call this octahedral. I'm going to try to draw in these 8 pyramid faces. First, we have one to the left. We have one in the back. We have one on the right. And we have one here in front. You can flip that and there are 4 more on the bottom, right? Here's one on the right, one in the back, one on the left, and one in front. So 8 faces, octahedral. All of those bond angles are 90 degrees, and so it's like we have this. Let's see. I'm going to draw it. I'm drawing black here. If you look at these equatorial positions, instead of being trigonal planar, they form a square almost, and so this is like a square pyramid on top and a square pyramid on bottom. Okay. SF6, sulfur hexafluoride, is a good example of this kind of molecule. Okay. Moving along and taking off some lone pairs here. The first lone pair we take off, it doesn't really matter, right? Because they're all 90 degrees. all positions are equivalent. And so we take one off. They put it at the bottom here just to show you that what's left over is a square pyramid. Right? So it's got this square base, and then it's got these four faces for the pyramid. Right? And so we have the square pyramid left over, square pyramidal. This lone pair at the bottom pushes all of these bonds up just a little bit, so they're just slightly less than 90 degrees. Right? When we go to pull off that second position, do you think it's going to be one of these equatorial positions here that are closest to the lone pair? Or do you think it's going to be this axial position up here that's farthest away from the lone pair? I hope you said the one that's farthest away from the lone pair. Remember, this is valence shell electron pair repulsion. And so the fact that the lone pairs will repel very strongly means that they want to get as far away from each other as possible. And so if we pull off two atoms and replace those with lone pairs, we end up with just some atoms, some bonds in that square plane, right? And so this is called square planar. Now we have a lone pair at the top that's pushing things down, and a lone pair at the bottom that's pushing things up. It turns out that since they balance each other out, we're back to being exactly 90 degrees all the way around. Right? They don't change, that bond angle doesn't change because those interactions are equal and opposite. Okay? Now, we could take some more electrons off of this. If we took one more off, then we'd be back to, I'm going to just cross it out here. If we took one more off, we'd be back to T-shaped, right? And if we took another one off, we'd be back to linear. And so those are just like what we saw with the trigonal bipyramidal. All right, so let's do a bit of practice. In order to predict this molecular geometry, you have got to be able to draw the right Lewis structure. And so if you had some issues in part 9b, make sure that you remedy those before our exam, because you're going to have to know the correct Lewis structure for a molecule. Then we're going to figure out how many bonding atoms there are and how many lone pairs there are for that central atom. So, ASH3, arsenic, comes with 5 electrons. Hydrogen comes with 3. Valence electrons, that's a total of 8. So we end up with something that looks like this as our Lewis structure. So there are 4 electron groups, okay, 3 bonds and 1 lone pair. Four electron groups means that it's tetrahedral. 3 bonds and 1 lone pair. Go back if you can't remember what this is, but this is trigonal pyramidal. And if we were to try to draw it correctly in the 3D sense, we would draw it something like this. Okay. OF2. Oxygen has 6 valence electrons. Fluorine each has 7, so that's a total of 14. So you have 20 electrons. Going to put O in the middle. A fluorine to either side. That uses 4 so far. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Remember, our rules say if we have leftover electrons, we've got to put them on the central atom, fill his octet. So there's our OF2. Okay. If we look around that central atom, again, we're looking just at the oxygen. He does have 4 electron groups. He's got 2 bonds and 2 lone pairs. He's still tetrahedral in terms of his electronic geometry, but his molecular geometry is bent. Now, it's easy to draw this linear, but we have to recognize that if we have 4 electron groups, 2 bonds, 2 lone pairs, that is a bent molecule. And so, really, he should look like this. Okay? All right. I'm going to jump down to E here. If you want to do C and D, feel free to do that. The answers to these are in your textbook. If we had C2H4, we've got 2 carbons. And since we've got 4 hydrogens, I'm going to just distribute those hydrogens around. Carbon comes with 4 electrons, so that's a total of 8. Hydrogen, that's 4, so there should be 12. We've got 10 electrons here. My rules tell me to put a lone pair on an atom, and then that brings me up to 12. The carbon on the left doesn't have a full octet, so I've got to make that lone pair into a double bond. And so I should have a geometry for both central atoms. It turns out in this case it's symmetrical, so they're both the same. But anytime you have more than one central atom, you should give the molecular geometry for all central atoms. And so for carbon here, we have 3 electron groups. Remember, a double bond or a triple bond counts as just 1 electron group. Each carbon has 3 bonds and no lone pairs. So that's trigonal, planar, and it turns out that because there's no lone pairs, the molecular geometry and the electronic geometry are the same, so they are both trigonal planar. Be careful that it asks for either molecular geometry or electronic geometry, because they could be different, as we saw up here, tetrahedral versus bent. Sometimes they're the same, like we saw with this one. And so if we tried to draw this in a somewhat accurate form, then these would both have trigonal shapes around them. And so that would be sort of the correct way of drawing that Lewis structure. All right? We'll come back and deal with some more of Chapter 10 in the next video. Take care.